Okay, so now let us look at another three examples regarding to series. So look at the first one, log n squared over n to the power 7s. Okay, so for this problem, there is a little bit tricky part. That is ln, so the logarithmic function. If we draw that, we know that the logarithmic function is something like this. Okay, in other words, this is y equals x. Okay, so this is y equals ln of x. So as we can tell that one of a inequality, what we can tell is ln x actually is less than x. Okay, less than x for x is greater than 0. So with this inequality in mind, what we can get is ln n actually is less than n. Okay, because this is the discretized format from this is continuous function here, but we only take the integers n equals 1, 2, 3, 4, etc. As you can see, this is true all the time. So since also those are both positive, let's set n starting from 1. Well, maybe we can say this is n starting from 2, because n starting from 1, the term is 0 over 1, which is 0. Okay, so we can let n start from 2. So as n is greater or equal than 2, this is true. So correspondingly, this is true also. Okay. So in other words, from here, for n is greater or equal than 2. So from this inequality, what we can construct is, okay, this series actually is less than n squared over n to the power 7s. Okay. Now look at what we have here. This actually it's n 1 over n to the power 5th. Okay. And we know that, oops, I think I should. So this is the same thing. So notice that this is a p, right, series with p equals 5. And we know that a p series, when p is greater than 1, then the series converge. So we know that this actual series converge. And then based on the direct comparison test, the largest series converge, hence our small series also converge. Okay, so we can get that this series, it converges. Okay, so in this problem, what I use this inequality to construct this series, and then the series I'm comparing is a p series and it's a convergent p series. Hence, based on this is called the direct comparison test, and then we can figure out that my original series converge. Okay, so the central idea is to use the direct comparison test, and then the comparing series is a p series, is a convergent p series, so series converge. Okay, so this is one example. The next example here, see, it's going to be a little bit different. Of course, guys, I'd like to let you know that to check whether a series converges or diverges, you have so many different methods. So the method I provided here, I think, is the most straightforward one, but it does not mean that it's going to be the only one. You have more than one ways to figure it out. Okay. Okay, so let's continue here. So limit n plus 6 over n plus 6 here. Now, in this problem here, as you can see, if we carry over the idea from the first example. I know that my series is true. Right? So based on this inequality, and this series actually is 1, okay? So this is, right, because log of n plus 6 is less than n plus 6. And it looks like this, you see guys, this series actually is diverged. But based on the direct comparison test, if the larger series is diverging, we don't know whether this series is converged or diverged. So the direct comparison it fails, okay? It fails. At least for this situation, it fails. I mean, you might be able to consider construct the other inequality that can show the series converge or diverge. But in this construction, I think, the direct comparison test fails. Okay. So what we can do here is we can try to think about it. Maybe we can give a try about the integral test. Okay. So to handle this with the integral test, let's think about this. How do we do this one? Now, if we gonna use this one as an integral test, now we have to show that my function, which is fx equals ln of x plus 6 over x plus 6. Okay. I have to show that my function, first of all, it is positive. Okay. Continuous. And then I have to show that the function is non-increasing. Okay, increasing. So I have to show those three conditions here. And it turns out that positive is for x is greater or equal than 2. Okay, positive is true, right? And continuous is also true. So all we need to check is my function is non-increasing, which I need to check that the derivative of this function, which is x plus 6 squared, right? Lower part times the derivative of the top minus top times the derivative of the lower part, which is 1. So it turns out what I have here is 1 minus ln of x plus 6. So it's very obvious that since x is greater or equal than 2, so the smallest ln function is ln of 8. Ln of 8 it actually is greater than 1. And so it turns out that the derivative of this one is less than 0 for x is greater or equal than 2. Okay, so maybe let's omit this function at this series at this moment. This is we can handle that in the next video here. And it turns out that so three conditions both satisfied: positive, continuous, and non-increasing. Okay, so all I need to check is I can check this integral. If this integral exists, so does my series converges. That is the integral test. Okay. And if my integral goes to infinity, so my series diverges. Okay. So the problem becomes, how do I evaluate this integral? So it turns out that, guys, you can use the integration by parts. So for here, I think I'm gonna omit this. So it turns out that This is limit b goes to infinity, integral from 2 to b ln of x plus 6 over x plus 6 dx, okay? So, because this is an improper integral for here. And it turns out the integral of this, you can use the integration by parts. It's gonna give you its ln of x plus 6, actually it's square over 2, okay, over 2. So if you, right, so you think you can evaluate this one easily. So use the chain rule. So it's 2 ln of x plus 6 times the derivative of ln x plus 6. So it turns out it gives us this, okay? So from here to here, I'm actually is using the integration by parts. Turns out, if I plug in to this, what I have here is ln of b plus 6 square over 2 minus ln 8 over 2, right? 8 squared and then over 2. And do you see that as b goes to infinity, actually this integral gonna goes to infinity, okay? So based on the integral test, we can claim that my original series diverges, okay? So here's a conclusion. Based on the integral test series ln of m plus 6 over m plus 6 actually is diverges, okay? So based on the integral test, my series diverges, okay? So this video is a little bit longer, and both of the series problem are a little bit tricky. First one using the direct comparison, and the second one actually is using the integral test. Keep in mind, to use the integral test, you have to verify those three conditions for the function positive, continuous, and non-increasing. Okay, especially for the non-increasing. Most of the time, if the problem is not that straightforward, take the derivative and then show that the derivative is less than 0, and then evaluate that integral to get your conclusion. Okay, so hope you enjoyed this video, and thank you for the watching.